Good evening, everyone. My name is Kunveer Singh, and the topic of my dissertation is breaking a glass box and designing a 24/7 IT office. So post-globalization in India, we have actually seen a rise in IT industry. The tertiary sector has been something which is the highest employer. Um, the commercial sector itself has been growing at a rate of 8% per annum, and out of which 70% of the spaces which have been developed as an office space have been occupied by the IT industry itself. 12 cities in the entire country, the 12 major cities of the country, have been considered as the development center or the hubs for the IT industry. And 53% of the global offshore market is actually present in India. But since the Western companies are coming in India, they are also getting their own form of design, which is this not climatic responsive design, glass buildings, big mass chunks of glass box, which are highly mechanically ventilated. Um, this is something which is like a typical layout of an IT office, which is occupied 24/7. Highly dense, the density of these spaces are almost 4.5 square meter per person. It is a very typical layout because they have like towers, which are connected with cores. So they have central cores with big, deep plans in which they just fit people in. So that's what their concept is in order to gain productivity. Um, an IT industry is basically, in terms of ownership, it's divided into two categories. One is an occupant category, which is based on the fact that the owner of the company owns the entire office floor or your campus. For example, Wipro or Infosys. The other is more like a core and shell kind of a structure in which you have tenancy agreements which are happening. So various companies take up different floors, and it's more like a vertically stacked kind of a layout in which you have maximum area which is taken up by the surface parking, and the remaining area is just a vertical rise of building. So my main concept out of an IT park is mainly focusing on the 24/7 office spaces. For that, in order to understand an IT office, how it works, uh, an IT office is basically divided into single shifts and multiple shifts. Multiple shifts have morning, intermediate, and night shifts, which are functioning. We did a pilot survey in order to understand how a 24/7 office space would work. Most of the offices work most of the shifts or people work 5 days a week because because most of the offices have four teams which are working at a particular time. Shift timings usually last 9 hours, and duration of break is something which is between 30 and 60 minutes. So night shift occupancy is something which is almost half as compared, or you can say it's quite low as compared to the intermediate and the morning shifts. The next thing which is really crucial in terms of an IT office which is occupied 24/7 is the internal loads and the equipment usage. Based on the pilot result, so we have hot sharing desks and personal desk spaces. The division has been significantly growing to, the hot desks are significantly increasing day by day. Uh, there have been studies which show that at this point of time, hot desks are 70% of the entire office space. Because they have more shared equipment. More shared equipment means that the loads are being divided amongst the users. On the contrary, in case of a personal desk space, you have individual equipment, so that's why a per desk load is quite high. So for my case, I am taking my site in the Delhi NCR region. The site is in Gurgaon. The climate is a composite climate with harsh summers, monsoons are really humid, and winters are cool, but during the daytime, the temperatures go above 20 degrees. The wind is something which is from the northwest predominantly, and during the summer months, it's dominant from the eastern side, but the daytime and the nighttime variation isn't much. So on an average, we have a wind of like 2 meters per second, but in the winter months, it's very low. So the next study was to understand how the temperatures have been divided, what is the frequency of a particular temperature in order to understand the comfort. So in summers, almost 40% of the time, we need air conditioning. And in winters, we would require about 58% of the time when the climate is out of comfort. But in case of a 24/7 office space, it's more about per hour variation rather than an annual kind of a comfort. So an effective temperature chart has been derived to understand per hour what is the temperature variation which happens. So for different shifts, like for example, the morning shift, which happens from 9 a.m. to 5 a.m., the hottest period is something which is between 1 to 3 o'clock in the evening, whereas the coolest period is at 9 a.m. On the other hand, the intermediate shift, which happens between 5 to 1, the hottest is at 5 p.m. and the coolest is at 1. So this was important to understand because based on this, we can actually derive our passive strategies. But there's one more consideration which needs to be done before we come to the design, that is the pollution levels. Delhi and NCR region have been having extreme amount of pollution problems at this lately, and this is something which is quite recent. The outdoor air quality is very poor. Even in the summer months, about 75% of the time, we have very poor air quality. That's because of the dust particles which are there. So most of the pollution in Delhi is basically because of 2.5 PM. And since we don't have a lot of wind, which is flowing during that particular point of time, so the particles don't really get dissipated from there. Apart from that, in terms of radiation, we have clear skies most of the time, whereas the cloud cover is basically during the monsoon seasons. South gets the least amount of radiation during the summer months, whereas good solar access during the winter months. So this is the site. The site is situated in the Cyber City, which is an IT hub, which has been developed in Gurgaon. The area of the site is 24,000 square meters. And the ground coverage needs to be 40%, and the FAR needs to be 250%. The maximum building height limit is 30 meters. And over there, I'm just showing the shading patterns on 21st of June, 21st of January, and 21st of March, just to show the regions which are overshadowed throughout the year. The site is well connected. It has a metro line next to it. The site has proper road networks around it. We have a surface parking, so we don't really need to provide surface parking on our side, which is an advantage. Apart from that, a good solar access, because the site is not in a very dense location except one tall building which is over there. Apart from that, the site does get good solar access. So now coming on to the context. In case of an IT park or a 24/7 office building, it is the energy performance of the space which is a question mark. Most of the benchmarks state that for a 3-shift office, the energy performance needs to be 450 kilowatt hour per meter square per year. Some of them, like for example, the Bureau of Energy Efficiency doesn't really consider that. It considers hourly, the number of hours of operation an office works. So it's benchmarking is based on that. But do the actual offices really comply to this? Not really. So we did a field work, and we figured out that most of the 24/7 offices have an energy performance above 600, and none of them really comply to the benchmark of 450. And that is because of the fact that all these offices are tenants, so they don't really have user controls inside their offices. Deep plans which have been developed by developers. So the percentage of cooling is 100%, and there is no division of space. So the next thing was, what are the kind of spaces in an IT office? So Offshore Development Center is the main space which has been occupied 24/7. It consists of an open plan, which takes up almost 75% of the area. Then you need to have one small cabin space and a huddle room. So that requires air conditioning because that has the maximum amount of occupancy density, and equipment usage. Then comes the finance center, which again is an open plan with high density. On the other hand, spaces like meeting rooms, breakout spaces, and training rooms are something which have been occupied not on a regular pattern, but these can be the spaces which can be passively cooled because they don't have a fixed schedule. So this is where we start the division of the office spaces in terms of spaces which require air conditioning and spaces which do not require air conditioning. For our field work, when we started, this was one of the cases which we took. So this became our base case. In order to understand the base case, the plan was divided into zones. First 8 meters was considered as the passive zone, and then was the active zone. So the active zone is a place where you don't have any kind of connection with the outdoors. And it's clear, like with a set point of 24, the temperature inside is maintained around 25 degrees, whereas in the passive zone, you still see a slight variation based on the amount of solar gains which you get, or because of the contact it has with the outdoor environment. The glazing ratios are usually 100% in the west, as you can see in the photographs. On the south side, it has 50%, so it has high glazing ratios. So yes, in order to match the field work, we had to like model it exactly the same. So these were the problems which we kind of figured out. Like, for example, the cooling set point was 21 degrees for this office space. The occupancy density and the equipment usage was very high. There was low thermal mass and change of glazing. So we just tried to like change a few things to understand what is the impact it has, and these are the impacts. So in case of a base case, which started in 962, just changing the cooling set point from 21 to 24, and from 24 to 26, there was sudden reduction. From 24 to 26 had a 9.2% reduction as compared to 21 to 24. Then the next thing was just changing the material of the walls, which was based on the ECBC and the windows. So in total, we can say that we can actually reduce up to 28% or 37% based on the cooling set point. The cooling set points which have been provided over here are based on the National Building Code for offices. So over here, you're seeing the heat gains in the offices and the cooling load offset for that, and how it gets affected by just changing the values over there. I'll just skip this. So yeah. After this, we develop the shoebox, because that is where we start with the daylighting analysis in order to understand the depth. For daylighting analysis, we did not take daylight factor. We took daylight autonomy, because in terms of daylight autonomy, we can actually understand the minimum lux levels inside the offices, and it also helps in the calculation of electricity used for lighting. So we took 30%, 40%, and 50% as the glazing ratios. Daylight autonomy, 40% glazing is something which performed well throughout. It had lux levels above more than 80% of the spaces were above 300 lux in all the orientations, whereas 50% also performed well. But in terms of useful daylight autonomy, the 40% glazing was something which actually performed better than the 50%. Whereas it's the west part where the 30% glazing still works well. We have high amount of useful daylight autonomy. But just daylighting wasn't the factor. We had to consider the heat gains through the windows. So the next part was heat gains through the windows, which came through, and 30% had the least amount of heat gains, whereas 40% had slightly more, but 50% was something which was way more as compared to 40 and 30. So overall, in terms of daylighting and thermal performance, 40% glazing was something which was taken. Now, the placement of the windows, this is an annual kind of situation, but it needs to be understood that the windows will perform differently for different kind of occupancy patterns. So we kind of checked what are the heat gains in terms of different occupancy patterns, like for example, from 1 to 9, from 9 to 5, and from 5 to 1. And so these are the orientations which work the best in terms of reducing the solar heat gains during the different occupant times. So based on this, our program will be divided and the office spaces will be oriented. So this is the site. Uh, Initial part of the site is considered as the circulation area. We do not provide any kind of surface parking over here. The surface parking, there's an adjacent surface parking, so that's why it goes over there. Rest entire parking will be in the basement. The gray zone is the overshadow zone, which we got from the shadow analysis which we did for the site. Okay, so what's the concept? So the concept of the design is basically 8 by 8 grid is something which is very common in an IT office. So we just took a tower of an IT office with a core in the center. We just took the cores, moved them to the sides, and expanded the building. Then we just stepped it outside so that we have an internal passage or an internal passage zone, which is like a courtyard. And so the active zones come on the outside, which require air conditioning, whereas the passive zones, which can do with the passive strategies, come towards the inside of the floor plan. So this is how a floor plan looks like. The cores are on the edges, and in between we have the courtyard. These are the offshore development centers. So one offshore development, minimum area for an offshore development center needs to be 150 square meters and for 60 people. So based on the standards which have been provided, these were made. So for our thermal analysis, there were two kind of occupancy patterns which were studied, because since it's more like a lettable area, we can't really have the occupants following our occupancy pattern. So one of them would be a rotational policy in which a different space has been occupied for a different shift. And another analysis was done for a case in which all the spaces have been occupied for a 24/7 kind of an occupancies in order to get what is the difference in the cooling load which you get. This is a space which is occupied only in the morning shift, so this wasn't considered for that. This is basically the financial center and the TV rooms. So based on 40% glazing, this is the kind of elevation which we got. The cell shading part is something which I'm going to talk next. So yes, in order to get the cell shading, which is showed in the concept, the forms were studied based on the orientation, the amount of shading which they provide and amount of radiation which they cut was studied. So that's why on the east, on the northwest and the southeast orientation, about a 2-meter overhang or a floor offset has been provided. And this provides a significant amount of reduction in glare. Not only that, but on the desk spaces, the lux level is around 300 to 500. And in the internal depths, because of those big glazing over there, we have a lux level about 500. So it's a well-lit space, not overly lit, not underlit, but it depends on the time of the day and which point we are actually occupying this space. So the next study for the active zones was the thermal mass which has been used. In order to reduce the cooling loads, various kind of thermal masses were tested. For our case, we took a cavity wall with 75 mm insulation. The 75 mm insulation was polyurethane insulation. Then the next thing was to understand the comfort in summers and the fall period, because that is the period when you require air conditioning. It is a must, because high internal gains and high outdoor temperatures, it is really important to cool the space down. So for that case, we tried looking at places with radiant systems. This is one of the cases which we studied for the fieldwork. The surface temperatures have been reduced to around 22, 23, and the air temperature inside the space is around 28, 29. So the occupants inside the space were quite comfortable. It's because the structure itself was quite cool, whereas the air temperature was something which is still in comfort based on the adaptive comfort bands. So if we had just the air conditioning and the mean radiant temperature at 23 degrees, we achieved like 46% comfort in terms of PMV. But if we just provided an elevated airspeed of 1.5 meter per second, through fans, we achieved almost 71% of the time, 71% time comfort during the summer months. Then comes the passive zone. In passive zone, security check rooms and the printer rooms, they don't really require any kind of air conditioning. So that's why they were put inside. Whereas the breakout spaces, the meeting rooms are something which are like mixed mode. So in terms of occupancy, if required, you can have your air conditioning on. So this is the section which we get. On the lower levels, we have the miscellaneous programs like the gyms, the other big server rooms, all were shifted on the ground floor, whereas the office spaces were on the top. In between, we have like terrace gardens because there's a lot of pollution. So you need to plant certain plantations over there to combat that kind of pollution levels. The courtyard itself was covered with a space frame. Initially, the space frame was just a normal steel space frame without any kind of reflector patterns, but later on reflector patterns were added. The atrium space has a water body for evaporative cooling potential because when the outdoor temperature is around 35 during the summer months, we have a diurnal, we have a wet bulb depression of almost 9 to 12 degrees, but since the efficiency is around 0.7, which we took, so that's why this is the estimated temperature we might get in our space. Is that the wet bulb? Huh? Is this the wet bulb? No. This is the temperature which we get for after evaporative cooling, not just the wet bulb. So this is the courtyard space, how it looks, with the cores on the sides. Next to a water body, we have like a temperature of 26 in section. So in order to supply the air into the courtyard, we actually take the air from outside, we put it into an earth tunnel. This is something which is more like an experimental kind of a thing. We put it into an air tunnel, and then we release the air inside the courtyard next to the water to cool it further. On the contrary, for the radiant system, we have a geothermal system in which we take the pipes down up to 8 meters. Because the temperature at 8 meters for our site is 25 degrees. So it cools down the water significantly. And then the water has been supplied into the active system or the active areas. So our reflector panels, when they were applied inside the space or the atrium spaces, the lux levels were brought down to an acceptable limit. So according to SIBSI and Indian standards, we need lux levels of 1,000 to 1,500 in an atrium space at max, and that's what we achieved. The reflectivity or the reflector panels covered approximately 50% of the entire space frame, and that's how we reduced the radiations or the lux levels inside. This is a typical layout of an ODC. So from 693, which we got from base case optimization, we started changing our design and modifying it. We came down to 322. This 322 kilowatt hour per meter square per year is something which is for a round occupancy in which all the spaces have been occupied 24/7. But if we take a rotational policy, then we come down to 287 kilowatt hour per meter square per year. But this value is just based on the air-conditioned space only. This does not include the area of the meeting rooms and the security, because in that case, the kilowatt hour per meter square will reduce. So yeah, thank you. That was slow.
Pablo's digesting this. Thank you. This was a really comprehensive story. I'm trying to match a few things that you've said. I totally understand the breaking the glass boxes. That's a good pursuit. I don't know why it hasn't happened around the world in the last 30 years that we've been saying we don't want glass buildings anymore. Actually, we do. We do want glass buildings, even in India. So it's sort of counter intuitive in terms of energy use and sunlight and daylight. But there is more, of course, happening in these spaces to those people than just their climatic condition and the amount of energy the building uses. People also have, you know, hearts and souls and things like that. And so I don't know whether it will happen, but in your study, it's a very good pursuit. I like the 24/7 idea, and Delhi is, I mean, it's notoriously polluted, and it's, if you can use the land better and materials better, and you can have the spread out the peaks of the city around the clock, then that must be a good thing. Also, it's interesting because, and somehow, I would have loved to hear some big sort of percentage changes in energy use or per, you know, per work hour or something, because you use the cooler parts of the day to work. You know, for half the day, you don't need to worry much about, you know, cooling, because it's, you know, but you also don't need to worry much about daylight levels, because there ain't such a thing in the middle of the night. So there is, I would be interested to see if we as societies drop the idea of, you know, having such strict work hours per day, and we shift it more around, and we work in the cooler parts of the day, that will be a big impact. And it's sort of, I don't know whether you have the data in this, in all the stuff that you've done to be able to find a percentage for that.
In the case where we talk about the rotation policy,
Yeah.
Yes, there's a division. For nighttime, we had the cooling loads down to almost 45 kilowatt hour per meter square per year.
Yeah.
Whereas the daytime was something which is significantly high.
Yeah.
It's around 170.
Yeah.
So that's the variation. That's the level of variation which you get, even in the same occupancy which you have.
Yeah. Yeah. I think it'd be interesting to include this as a,
Right.
maybe even a separate sort of paragraph in your book to explain the benefits of these big points that you made in the beginning. Yeah, I thought this was very, very interesting. I'm, as always, not quite following all the numbers. I'm trying very hard, but it's a tough thing. And but it looks like it's all really well considered, and it's all bringing solutions, you know. So it sort of looks great. Thanks.
Thank you.
Yeah, I think we're ready. But I'm going to just make some very specific points. I was interested in the last presenter and yourself referring to the pollution problem in smaller cities. But there's a lot of work done on looking at the migration of pollution, which after all is primarily from traffic, road traffic. Road traffic is on the ground level, and it runs in very specific places. Yeah. And as we know, the wind does very interesting things as it blows over the urban surface. So there's been quite a lot of work done quite recently on looking at the migration of pollution upwards. So this is perhaps a case for taller buildings, and it certainly might be a case for making buildings partially air-conditioned where the pollution levels are high, and then allowing more natural ventilation to take place higher up. In other words, don't just write it off because it's very polluted in the street. That's the first point. Right. The second point, with this multi-shift working, we really do need a new index on energy consumption. Yeah. And that should be something like energy consumption per employed person hour, or it should be possibly just the wattage of a person. In other words, we generate 100 and odd watts, but we also consume around about 15, I think. Yeah. And it'd be very interesting to know what our wattage consumption is when we go to work, when we're at home, when we're on holiday. All of those things would be very interesting. But we really can't go on talking about these numbers in buildings. We're just not comparing like with like. We have a target which is we're as fixed for a certain type of building, and then you cleverly allow this to have multiple shifts and warm desking and all of those things. And of course it makes it very difficult to make a comparison. So I do think there are this idea of 24-hour working is interesting because it does have some real downsides. One of those is the impact on the workers. And I've just been looking into some work done whereby night working is now regarded as a cancer risk for people. And that they're saying that we actually need more light for night workers than we do for day workers. Now, the reason is very simple. When the person came to work in the morning, they got a really big dose of very bright light, and that got the old clock going in the head, you know, the circadian rhythm, it established that. And it doesn't really matter then what happens to them for the rest of the day. But people that work all night need to have their daytime clock switched on. So they need higher levels of light while they're working. So that's a bit of a downside. The other thing, just another specific point, I was interested in your internal courtyard, and then it sort of became an atrium. It had a space frame, which is an expensive item, and I wasn't quite sure what was hanging on that space frame and how that interfered with the lighting of the spaces down below.
So it's just normal reflector panels, just to cover the openings so that there's a percentage of light which is coming in, that's it. To give, this is one of the cases which is there in one of the buildings in India. The Indian Habitat Center has
But
it.
are they fixed? Do they?
Yeah, those are
they
those
primarily
are
there to reflect light down and increase the illumination in the atrium?
No, they are to reflect.
To reduce it?
Yeah, because otherwise we get excessive amount, because the width is about 16 meters.
Yes.
So that's why we get excessive amount of lux inside. So we need to reduce the amount of lux and the radiations.
Okay. And does that change the distribution of light so that the lower part of the atrium gets more light and the upper part gets less? Is that possible to do? Okay, well that's good.
Patrick will explain that later.
Right. and this wall here, I don't quite...
That's the core.
That's the
core, the lifts.
So this is no part of the evaporative cooling, because you started talking about evaporative cooling.
No, this is not the part of evaporative cooling.
Right.
It's because we have like air flowing in from below and from the sides to allow natural airflow from the ground levels.
And where does the evaporation take place?
Over here next to the water bodies and below the water bodies, there's the air passes from the water. So it's a direct surface contact.
Evaporative cooling really only works when you have a very large surface area. So have some fountains in there and some mister sprays like they used in the Expo, which don't cause wetting because they evaporate so quickly that the drops are so small they evaporate before they hit anything.
Right.
And so because that, just the surface of a water, the amount of evaporation is very small and it won't really cause a great deal of cooling. Anyhow, thank you very much. As you can see, I was very absorbed by all of your technical ideas. Very interesting. Thank you.
Thank you.
Thank you for your effort. I think you made so much work that some of the ideas that you talked about are almost worth a thesis in itself, like the labyrinth or just addressing the occupancy and occupancy type and the shifts. That's super complex, and I think you have tried to touch in so many things. At some point, it's difficult to follow. The two things which I think are clear, almost clear to me, are one is the last slide that shows a summary of the 5 steps that you took and what is the impact in terms of the energy consumption. That is, I wish all the slides were like that one.
Okay.
Just to, I think it's good for you, it would be good for you to structure your final booklet with that mindset, like in delivering clear messages. The other thing that I found clear is your initial assessment. So you mentioned one is the glass facade, that is a general issue in many office buildings in India. The other one is the density of occupancy and the fact that most of these buildings are open plan. And if you had a cellularized space, if it's not fully occupied, at least you can only cool certain parts of the building. That would drop the cooling load substantially, the energy consumed by the building substantially. You said that. Also, as the cooling set point, it doesn't necessarily need to be 21 degrees. And the other one is the thermal mass. I think if your presentation, you took these 5 items and you hit one at a time, really clearly, and then the last slide is a summary of those 5 elements, it would be really clear. But these 5 items I just mentioned are not the last 5 that you show in your, so it was like going
Okay.
up and down. It's a bit, sorry, but I've struggled with that, and I think that just as an advice, I think you should
Okay.
try to make an effort in your communication. But I think overall, I think it's really interesting, and I enjoyed it. I think there are some items which I particularly enjoyed, like the way you approach your facade with this setting back of the. So there are some design intentions which are really good.
Thank you.
Well, it's again good to see the progress. I was following this project quite closely, so I'm quite familiar. So unlike other presentations, I can't comment on the pace, speed, or amount of material presented. So, but I know that it's been a huge challenge because the topic and the building type and the climate were so difficult that one of the questions was how bold one could get, or how far one could go while being realistic, because, well, we know that the density was a big issue, but then the density couldn't be reduced to a great extent. There were many limitations, but I think that overall, I mean, the story is quite convincing, and the process is quite rigorous, and it's quite believable that because it's not neither too conscious or over optimistic, and I think that's a good thing.
I was quite interested at the comparison I thought you were doing between glazing ratio and orientation, I think, and then there was the daylight autonomy, and at some point I thought that what you were trying to do was to see whether there were trade-offs between the glazing ratio and the daylight autonomy. In other words, whether we actually wanted the daylight that much, or was the daylight negotiable in the sense that having large windows meant a larger penalty in that climate with the 45 degrees than the gain in terms of daylighting, which perhaps was not very large anyway, since they didn't necessarily appreciate it. Some of them didn't appreciate it because they could have done with less, and others didn't need it at all because it was the night. But so I got very excited and interested, but I failed to follow beyond a certain point. I wasn't quite sure whether you were doing that. So that was one question that has remained in my mind, and perhaps in the book you can make, some note to clarify. The other thing was about this evaporative cooling, and this is where I asked you about that temperature in red, whether it was the wet pulp temperature. It could not have been anything else than the wet pulp temperature, because we couldn't possibly, go below that. I mean,
No, I know. This is not the wet bulb. Wet bulb is way below this.
Well, it can't be that. I mean,
So this is based on the wet bulb depression. The outdoor temperature minus.
Yes. Well.
So yeah, this is just 0.7 times that. So the wet bulb is below this.
The wet bulb is below this.
Yeah.
Well, I would have liked to see how below this it would have been. So then, yeah. So your answer was that this was the temperature reached as a result of the evaporative.
Yeah. A potential temperature which we can reach.
Well, I mean, I don't know. Huh? I would tend to doubt.
Right.
I would tend to doubt that. And my final point is about the sequence of the reduction in the loads, which from the 690 down to the 200 and something, or 300. So then what is the breakdown of what we are left with? And why can't we go below this? Is it that at that stage the cooling load is just the people?
No, it's because people plus equipment. Equipment density is quite high in an IT office. So there's a particular point after which
but
reduction
still,
in that.
you see, the people there, we have 100 watts per person in an area which I think you made to be 1.5 square meter, yeah? So, is it?
I didn't get you.
1.5 square meter per person?
2.5
2.5?
square meter. No, it's actually 4.5 square meter per person, and it's 2.5 square meter per workstation. So that's the density.
So we have 40,
required.
40 watts per square meter
Yeah.
is the metabolic, and well, the lights and the computational stuff is not as high as that. Will be less than that. So essentially what we are paying for
Is the
is
density.
for being there.
Yeah.
Okay? Well, I think it might have been mentioned also by Nick that, you know, that in itself alerts us to a cost of being there at that density.
Yeah.
That becomes quite recognizable in numerical terms. I mean, we could have made arguments about such density not being hygienic and all sorts of other things, but perhaps that point would not have gone that well with developers and so forth. But here, perhaps there might be a way of addressing, because then being able to reduce the density on the basis that becomes universally acceptable, or in any case financially acceptable, then opens up other avenues that, you know, allow you to go well beyond this 300 kilowatt hours per square meter.
The main challenge, which I think, is that since initially I just explained that in an IT industry, the offices are divided based on ownership, that one of the thing is that the developer develops the office and the tenants take it up. So the cooling loads or the electricity loads are actually divided between the tenants. So the developer doesn't really care about how many people you put in, and neither does the tenant, because for them it's less space in which they can actually operate. So that's why this is the density which offices have been following. So I was taking like the maximum or the worst case scenario which is happening right now for the analytical purpose. But yeah, initially I did do a comparison of the density ratios from 4.5 to 6 to 8. 8 is something which SIBSI states. But yeah, I did the comparison, and yeah, density does have an impact. So,
well, maybe, you know, that we'll find something equivalent to the to chicken, you know, free range, to bring the density to the free range.
We must build that into our index of performance we were talking about, not just talk about square meters, because the way of lowering energy consumption per square meter would be just to have 6 people in there instead of 600. So clearly that we must get a better measure.
Gunvir, thank you so much for not rushing this time. And I just need a clarification. I know Nick has asked about the covering of the shading. Is it fully glazed?
no.
No, so it's a special glass, but it's open.
It's not glass, it's a space frame. It's just a metal frame with reflective panels in between. That's it.
Okay, okay. So this was one clarification. The other clarification I would like to have, sorry if I missed it, you have this shape because it's, and you call it self-shading, but there is this inside shape which doesn't seem to be self-shading. How, I missed how did you
Shading
approach?
is for the areas which are actively cooled, so
Okay,
that
so-
there is reduction in the heat gains.
Yeah,
the
and
solar heat gains,
these
and
areas are what? I
the
did
main
miss.
ODC spaces which are running 24/7. The internal spaces are the
Yes.
spaces which are like the meeting rooms or the breakout spaces which don't require air conditioning, with a more adaptable kind of a comfort range over there because the internal loads are quite low. So you can have like passive strategies which are working over there.
Yeah, but you still want to avoid direct solar radiation.
But it's more like an ambient kind of a space rather than.
Okay, but are you addressing this in your book?
Yes.
Okay, thank you. Thank you.
Thank you.
much.